Okay. Good to go.
Okay. Hi, everybody. Thank you for joining our this week's Geoscience and GeoEnergy webinar. It's the 11th of February this year. I'm Maren Bremer from TU Delft, and I replace Hadi, who has teaching duties today and cannot make it. It's my pleasure to host you all together with Sebastian again from Heriot-Watt. We are especially grateful to our keynote speakers who accepted our invitations before and also today, and for you all joining us this week. And please subscribe also to our YouTube channel so you can see the upcoming talks, which might be quite interesting. To our students, we still invite you to join the Porous Media Tea Time talks to share your research and to broaden your network. Today, we are especially pleased to announce our keynote speaker of this week, Dr. Sabine den Hartog. She's associate professor at Heriot-Watt University since August last year. But also before she was with that university in Edinburgh since 2 years as assistant professor in the GeoEnergy group at the Lyell Center, and also affiliated with the Institute of GeoEnergy Engineering. Before that, she was in Liverpool as a Marie Sklodowska-Curie Research Fellow as a postdoc. And then before that, she spent her postdoc time in Utrecht in 2015 and at Penn State in the US as a National Science Foundation postdoctoral fellow for the GeoPrisms fellowship. Sabine obtained her PhD from Utrecht University in the Netherlands in 2013. She worked in the high pressure and high temperature laboratory over there. Her research focuses on geomechanics of subsurface energy systems, and in particular on the frictional behavior and slip stability of fault gouges. So her aim is to better understand both natural and induced seismicity, and she determined that with the understanding conditions and microcell deformation mechanisms. So that I think we also hear a bit about today, leading to stable and unstable fault slip and reactivated faults. She uses laboratory experiments and microstructural investigations and microphysical modeling. So it's our pleasure, Sabine, to host you today in our webinar. To the audience, her talk will last about 30 minutes and followed, like always, by questions and a discussion. So please type your questions in the chat, and Sebastian will go through them after the talk. Sabine, thanks once more to be here, and the stage is yours.
Thank you very much. Thank you for this introduction, and also thanks very much for inviting me to give this seminar. So today I will talk about the microphysics of fault frictional behavior. And why are we interested in fault frictional behavior? Well, to understand that, let's have a look at this diagram that shows a variety of geoenergy operations, such as CO2 storage or energy storage, the extraction of natural gas, or over here, an enhanced geothermal system. So all these subsurface energy systems, they affect the state of stress in the subsurface, and that can produce new faults, or more commonly, if they're pre-existing faults, they can cause slip along those faults, so they can reactivate the faults. And movement along faults that may result in earthquakes or induced seismicity. Let's look at some examples of induced seismicity in geoenergy applications. So this graph shows the injection pressure with the black line here, and the associated seismic events with the colored circles at a geothermal site in Basel, Switzerland. And seismic activity in this reservoir increased with rising pressure and flow rate. And in 2006, a magnitude 3.4 event was induced, and that eventually led to the abandonment of this geothermal site in 2009. More recently, in Pohang, a magnitude 5.5 earthquake was concluded to be related to a geothermal system. Also, natural gas production can lead to induced seismicity. So this has been seen, for example, in the Netherlands, in the northern province of Groningen. And a magnitude 3.6 event occurred there in 2012. And it has been decided that the Groningen gas field will be closed in 2020, even though the gas reserves are not there's still gas reserves there, but it's the induced seismicity which has led to the decision of closing this gas field. Also, things like wastewater injection related to oil extraction can cause induced seismicity. For example, a magnitude 5.8 earthquake in Oklahoma. And finally, as example, magnitude 2.3 event in Blackpool in the UK was the result of hydraulic fracturing tests. So, of course, also understanding fault frictional behavior is also relevant for natural seismicity. How can geoenergy operations cause fault reactivation? Well, the key point is that fluids at pressure, they are either injected, like here in this geothermal setting, or they are extracted from the subsurface, and that can change the state of stress of the subsurface in various ways. This diagram, a typical Moore diagram showing the shear stress and the normal stress, this is an example of one of the ways in which the state of stress can be changed by fluids at pressure. So this half circle here, it represents the state of stress of the subsurface. And when pore fluid at pressure is injected, one of the things it can do is it can just translate that state of stress towards lower effective normal stresses. And that then can lead to that a failure criterion for fault reactivation or creation of new faults, that is satisfied. So that's how you can get induced seismicity or fault reactivation, I should say, due to geoenergy operations. So in the title, I talk about microphysics of fault frictional behavior. But faults are kilometer scale structures. So why are we looking at the micro scale? Well, that is because it has been observed that within these very wide fault zones, the behavior is typically very much localized in something which is called a principal slip zone. And that consists of a comminuted material, so it's ultracataklazite, or a gouge if it's cohesionless. And in this diagram, this shows as a function of depth, the slip zone thickness. And for ultracataklazite principal slip zone, thicknesses of down to, well, below 1 millimeter have been observed. For gouge zones, also they are below 1 centimeter. So this is all very narrow, so it shows that the deformation is localized in fault zones. So to actually understand then the behavior, the full-scale behavior in nature, we are going to look at what happens at the grain scale to understand that better. I'll be focusing on phyllosilicates in this talk. Phyllosilicates, they are also known often as clays, and they are platy minerals. They have a short dimension here in a vertical direction and long dimensions horizontally and also perpendicular to the screen. This is an electron micrograph of some phyllosilicates, and you can also see here that they are platy in nature. And it is observed that faults are often localized in phyllosilicate-rich layers. So that is why I will be focusing on phyllosilicates in this talk. To understand fault frictional behavior better, we follow an approach consisting of several steps. Informed by nature, we perform experiments on fault materials, and then after such an experiment, we recover the sample and look at the microstructural characteristics. Based on the observations we do on those microstructures, we can then define a microphysical model in which we quantify the behavior observed, and that can then be used by modelers to make some predictions of how faults in nature could behave. So let's first look at the experiments. For fault friction experiments, we typically use the fault gouge material. So that's the crushed up rock material that you find along fault surfaces. And it's shown in red in these three possible setups here. The fault gouge is sandwiched between slider blocks, and it can be of various configuration. And those slider blocks are then held together by a normal stress in all these cases. The forcing blocks are then moved relatively to each other. So in this case, in the biaxial shear setup, the central block is pushed down while the side blocks are supported. In the rotary shear configuration, one of the sides is held stationary, whereas the other side is rotated. And in the direct shear setup, the entire assembly is shortened, and these two gray bits here, they can deform elastically. The stress that is needed to cause this deformation, the shear stress that is measured, in the rotary shear configuration, it is derived from the torque, which is measured as the distance. And once we know the shear stress, if we then divide the shear stress by the normal stress that was applied, we get a quantity known as the friction coefficient, written as mu, and that says something about, is basically the strength of the fault gouge. So these sliders then, they are, during an experiment, they are located in a shear apparatus. And the first thing you need to do to place such an assembly in a shear apparatus is to jacket it. So usually jacketed by a jacket made of rubber. And that is done because the assembly is located in an oil-filled pressure vessel. And the oil in here, it is pressurized, and that then applies the normal stress to the shear assembly. The typical pressures used here are of several tens to maybe over 100 MPa, so it's relevant for upper crustal or maybe even somewhat deeper conditions. So also the vessel is typically jacketed with heating elements, or there are heating elements around the pressure vessel, and with these the entire assembly can be heated up, and the experiments can be performed at temperatures relevant for the subsurface. This assembly is then located in a press, and in this case the bottom of the press moves upward. This then causes the deformation of the sample, and the shear stress is measured here on top via a load cell. And this, the speed with which this bottom is moved up, that can vary. This figure shows some typical data produced by shear experiments. This is a graph of the friction coefficient versus the shear displacement. This is data for a phyllosilicate muscovite deformed under wet conditions at 3 different temperatures. And so one of the important pieces of information that can be derived from this figure is the absolute value of mu. So in this case, it's between about 0.3 and about 0.7. So that is the strength of the fault gouge, and that tells you how easy it is to reactivate a fault. So in this case, the strength actually increases with increasing temperature, so from 200 to 400 to 600 degrees. And these temperatures, they are a bit more relevant for natural earthquakes in this case. If we look at room temperature data, so this is data for Moore and Lochner, this is for a variety of phyllosilicates, so micas are phyllosilicates. And it is the same type of diagram. It shows the coefficient of friction versus actual displacement. And if we look at the muscovite example, so the solid line, what we see here is that there is this decrease in the friction coefficient, which is related to a change in the conditions of the experiment. So when water was introduced, the friction coefficient decreased a lot. So water decreases the strength, and that's actually the case for all the phyllosilicates shown here. That effect of water on the phyllosilicate strength can also be observed in this graph, which shows coefficient of friction on the vertical axis, and now it is the relative humidity on the horizontal axis. A relative humidity of 0, meaning dry conditions and a relative humidity of 100, meaning wet conditions. This is data from the literature, from various papers, and it's data for several different phyllosilicates at room temperature. What this experimental data shows, though, it's a reduction of the friction coefficient with an increase in water content, increase in relative humidity. So that is corresponds to what we saw on the previous slide. If we look back at the figure that I showed to you before, so the muscovite data here, then you will probably have noticed that there are steps in the friction coefficient. These steps, they are related to changes in the slip velocity, so the velocity with which the forcing blocks are moved with respect to each other. This tells us something about the stability of sliding. So how the friction coefficient changes with that change in slip velocity tells you how easy or how likely it is that a reactivated fault causes seismicity. Because a fault, when it's reactivated, it doesn't necessarily result in an earthquake. So how should we interpret curves like this? Well, that's explained in these figures. The top here shows a stepwise increase in the slip velocity, and the bottom curve shows how the friction coefficient responds to that. In one of the possible types of responses, you have an instantaneous increase in the friction coefficient, followed by a more gradual decrease to a new steady state value. In this case, the new steady state friction coefficient is higher than the initial one. So that when the velocity went up, the friction coefficient went up. So this is known as velocity strengthening behavior. And we quantify this with a so-called rate and state friction parameter, A minus B, and that is positive for velocity strengthening behavior. You can imagine that if a fault gouge becomes stronger when you try to move the fault faster, that it will stop eventually, so you do not get earthquakes for velocity strengthening fault gouges. There's also another type of response possible. So we have the same stepwise increase in slip velocity here. Again, the friction coefficient increases instantaneously, but the final friction coefficient here is lower than the initial one. So for an increase in velocity, the friction coefficient goes down. We call this velocity weakening behavior. And this rate and state friction parameter, A minus B, is negative for velocity weakening behavior. In this case, if a fault becomes weaker, if you try to slip it faster, it can go faster still. And if it then becomes still weaker, it can go still faster, etc. So you can get some type of runaway behavior for velocity weakening fault gouges. So in this case, there is a potential for earthquakes to be generated. This figure on the right-hand side also shows velocity strengthening versus velocity weakening behavior. So here we plot mu on the vertical axis and velocity on the horizontal axis. And as the name already says, velocity strengthening behavior gives here a positive slope, whereas velocity weakening behavior, it has a negative slope. So this is A minus B, so that was this rate and state friction parameter, A minus B data for muscovite gouges at a variety of temperatures. And what we see here is that the A minus B value is predominantly positive. So that is predominantly velocity strengthening or stable behavior for muscovite under these conditions. This graph here shows the coefficient of friction versus the slip velocity. So it's basically the equivalent of this schematic figure here. And the data points here are literature data for muscovite, illite, or biotite at room temperature. It's a little bit hard to see because of the scale of the figure, but these data points actually show some rough slight positive trends of the friction coefficient with slip velocity. So that's again velocity strengthening behavior. Okay, so the next step in the approach is to look at the microstructures generated during the experiments. And some typical microstructures are shown here for muscovite on the left-hand side and biotite on the right-hand side. In both cases, what we can see is some more coarse-grained material in sigmoidal domains surrounded by finer-grained material. So that's in both cases. So the shear strain accommodated by deformation within the sigmoidal domains will be limited because they're disconnected. So it's more likely that behavior actually is localized in these in the through-going shear bands that surround the sigmoidal domains. If we zoom into those shear bands, we can see things like grains catching on each other, overlapping grain edges. If we zoom in further to the grain surface, then we can see cleavage ledges, so stepwise steps on the grain surface. If we zoom in further still, so this is an atomic force microscope image of muscovite. This is the topography of the sample, and here we can see that it is not a flat surface. There is a certain degree of roughness on it. This figure shows a summary of the different types, the different scales of interaction that could potentially control the strength of phyllosilicate gouges. As I mentioned, the shear strain accommodated by deformation of the sigmoidal domains is limited. So we assume that that's not the scale at which the strength is not the scale of interaction that controls the strength of phyllosilicate gouges. Is more likely to be the grain scale, so things like the edges of the grains catching on each other. The resistance offered by the cleavage ledges on the grain surface, they actually provide similar or lower resistance than what happens at the grain scale, so we don't really need to consider this one. And then we'd also do think that what happens at the atomic scale also is important for the overall resistance to sliding. So we assume that the strength is controlled by what happens at the grain scale and what happens at the atomic scale, and that both processes act in series. So the next step is then to make a microphysical model of this assumed deformation behavior. So this shows the model microstructure where the behavior is controlled by slip along the atomic scale planes here, so along the grain surface, grain interface, plus the strength to overcome the grain edges catching on each other. The first thing to describe a microphysical model of this, or to formulate a microphysical model, is to actually write down expressions for the microstructural parameters. So in this case, a crucial parameter is this overlap height C, and we assume that that is the result of normal compression of the aggregate under the action of the effective normal stress by linear elastic processes, so it's related here to Young's modulus. And the other important parameter is the size of the pores S, which is related to the porosity here. Then the next step in deriving the microphysical model is to write down an expression for the shear strength. And the shear strength in this case is it's the sum of the shear resistance due to grain interface sliding, so which is related to the roughness here at the atomic scale. It depends on the atomic scale friction coefficient. And the other term that should be taken into account to calculate the total shear resistance is the term related to the shear resistance due to the grain edge barriers shown over here. To actually calculate this, we need to find an expression for the sigma h, and sigma h, that is the normal stress acting on the interacting grain edge contacts or barriers. And what we have assumed in our model, so this is the model developed together with Dan Faulkner and Chris Byers. So what we have assumed is that under dry conditions, this grain edge barrier is controlled, the strength of that is controlled by critical edge crack growth, which occurs along the basal cleavage planes. And this is, so basically this is a critical crack extension, and it can be described by a Griffith criterion, and it depends on the specific surface energy in vacuum. Under wet conditions, on the other hand, then we assumed that this grain edge barrier strength is controlled by subcritical edge crack growth or stress corrosion cracking, and that this is actually controlled by this equation, which is a classical theory of rate processes. So this is the subcritical crack growth velocity. This can then be combined to get a relationship between the slip velocity, between the normal stress on the grain edge, and between the cleavage surface interfacial energy. So I should probably stress that out. This rate equation for subcritical crack growth, it depends on the cleavage surface interfacial energy, and this has a link to the relative humidity. So this can then all be used to predict the friction coefficient of phyllosilicates under various conditions. This is a figure which you've seen before. You've seen the, so this is mu versus the relative humidity for literature data. I've now added model predictions for several different assumptions for the atomic scale friction coefficient and different porosities. The absolute value of the friction coefficient, it varies depending on the parameters chosen, but what all the predictions do show is they show a decrease in the friction coefficient with an increase in the relative humidity, which is similar to what the experimental data showed. This is also a figure which you've seen before. So this was the friction coefficient versus the slip velocity. And again, it depends on the parameters chosen, but the model does predict positive values for the, it predicts an increase of the friction coefficient with slip velocity. So it predicts velocity strengthening behavior, which was similar to what experiments have shown. So phyllosilicates do not seem to be related to unstable fault motion, but they're still important to understand both stable and unstable fault behavior, because they are important components of microphysical models in which there's a mixture of minerals, and those models might predict both unstable and stable behavior. So this is an example here. This shows temperature on the vertical axis, or depth, and A minus B on the horizontal axis. The triangles here are experimental data for illite quartz, fault gouges, and the solid lines here are model predictions. This was a model in which there was a combination of both quartz and phyllosilicates. But the important thing here is that the model predictions of this model didn't actually match quite that well at low temperatures. That was because there was it assumed a constant friction coefficient for phyllosilicates. Now with the model that I just showed you, if that is incorporated in this model, that fit can actually be improved. So that's how the phyllosilicate model can be used in other models. So the final step is then that modelers, they can use these microphysical models to actually make some predictions for behavior on fault scales. Sometimes we find a remarkable correlation between experimental results and natural behavior. So I'll show you some results of work that I've done together with Marion Thomas and Dan Faulkner. So we looked at samples from the longitudinal valley faults in Taiwan. So this fault, it has generated some earthquakes, and the interesting thing is that it is locked in the north. So that's shown by these dark colors. It's locked in along the northern section, whereas it is creeping in the southern section. We took samples, 3 samples from this locked part and 2 samples from the creeping part, and we performed experiments on these fault gouges. What we found is, and here we have the typical graph again of friction coefficient versus load point displacement. We found that there was a very clear distinction between samples from the locked section and samples from the creeping section. So the samples from the locked section, they typically had higher friction coefficients than the samples from the creeping section, and they also showed these clear peaks upon velocity steps which were absent for the samples from the creeping section. Also, in terms of A minus B behavior, we saw a difference. So this is A minus B versus temperature, and the color coding of the samples here is the same as in this figure. So the green and the blue samples are from the locked section, and they showed a decrease of A minus B, or remaining slightly sort of neutral to slight decrease with increasing temperature, whereas the samples from the creeping section, so the purple and pink triangles, they actually became a bit more positive with increasing temperature. And interestingly, when we add data, A minus B data inferred from geodetic analysis, that actually fits really, really well with the experimental data. We still are in the process of actually trying to understand this behavior. It may have something to do with the distribution of kaolinite in these samples, and it's absent in those samples, but that's work in progress. So finally, at Heriot-Watt University, we are currently investigating the frictional behavior of granite fault gouges. So that's part of the NERC-funded GeoEnergy project, and this work is done by postdoc Nathaniel Forbes-Inskip and PhD student Nick Harpers. This project is related to the United Downs Deep Geothermal Power Project, which uses a permeable fault zone for the circulation of geothermal fluids. And we are investigating how such fluids might affect the granite composition, as shown here, and what the possible implications are for the frictional properties. Okay, so that brings me to the conclusion. To better understand induced or natural seismicity, we need to understand fault frictional behavior better. Fault friction is controlled by processes at the grain scale. And we studied those grain scale processes via a combination of experiments, microstructural investigations, and microphysical modeling. And microphysical models then allow for extrapolation of lab to nature. Thanks very much.
Dear Sabine, thank you very much for this great talk. I think it was very inspiring and I learned a lot. There are some questions I would have, but I give the floor to Sebastian first to chair the question and answer session.
Yes, thank you very much, Sabine, for a really excellent talk. And so we have some first question. Please do enter your questions into the chat room. So for Sabine, so the first question is from Youssef, thanking you for the presentation. And he wonders if studies have been done that focus on fluids with lower kinematic viscosity, like CO2 instead of water in the experiment. Would that change fault frictional behavior?
If I say this correctly, this has been done. It's not actually been done by myself, so I can't really comment on the results of those studies. But I know that at the high pressure and temperature laboratory in Utrecht, they have used different types of fluids for fault friction experiments. So I would definitely look up their papers, but it's not something I have experience with myself.
Okay, so there's some reading for Youssef to do then. A question from Anne, again, thanking you for the presentation. Thinking about these microphysical models, I have to ask a Groningen question. How to adapt them to adjust for the mixtures with anhydride that Luc Hounfeld showed to be most seismogenic?
So that's a good question, Anna. So I think that. So let me say this correctly. I think I'm going to relate this a bit to the model that I made myself for mixtures of quartz and phyllosilicate. So I'm not quite sure whether it's anhydride mixed with anything, but I would say that pressure solution is a is a vital component if you want to make these models for anhydrite. So you would get time-dependent behavior in there. So it's something that requires a bit of thought, and I can't quite tell you now how to adjust the model exactly, but you would definitely get time-dependent behavior in there that will then affect the results. But yeah, I'm sure it can be done. I'm sure of that.
Okay, thank you. So picking up on Ant's point, there's obviously a lot of complexity in terms of the mineralogy. Ant's and Yusuf's points, there's a lot of complexity in terms of the mineralogy, the exact mineralogy, fluid compositions, the change behavior. So you show very nicely how these really advanced experiments give us better models. But then how do we use actually these models to assess the risk of induced seismicity, given that we don't know that much about the surface, so about the subsurface? I'm asking as a sort of very pragmatic engineer here, what do I need to put into my models to assess the risk of induced seismicity, given that I know so very little about the subsurface?
Yeah, so that's a good point. I think that the communication with the geologists is probably quite vital there. You need to have some idea about the materials that are present in the subsurface, because so what is often done is some rate and state friction parameters, so values for the strength of the fault gouge and values for this A minus B parameter, they are just some assumptions are made, or they are directly taken from experiments, which is not well, that actually misses that extrapolation step. There's no basis to use empirical data for those predictions. So I think that this is a step forward. If you know what the mineralogy is, then you can use the right predictions of microphysical parameters, but it doesn't actually solve the problem of knowing what's down there. I think that's we need to know that to be able to use the right microphysical model.
Would there be an opportunity, or maybe a practical approach, is to just run more models, more simulations, look at sort of within the range of what could be down there, see what behaviors we can expect, and use that to map out risks and probabilities and likely.
Yeah, I think that's an option. I think it's also probably important to, and we've done that a bit, to basically get the trends out of the experimental data and then quantify those with the microphysical models, because as long as you know the trends, then you can do a certain amount of extrapolation to the natural conditions.
Okay. It is quite relatively quiet in the chat room at the moment. So if our audience does have further questions, please do enter them. Maren, you mentioned you had a question for Sabine as well.
I wonder, Sabine, due to my background in geothermal, and I have been working in high enthalpy geothermal fields, and there we have much more clay minerals in the subsurface due to alteration. So faults in these high enthalpy geothermal systems, do they face a higher risk of slip, of induced seismicity probably, or?
So because you say they typically have more clays?
Yeah, due to the alteration of the geothermal fluids within the rocks,
so
higher temperatures, higher pressures.
So I don't really have enough data to really say whether the risk is higher. The thing that I can say though is that from the experiments that we have done, it does seem that clays or phyllosilicates typically show more stable type behavior. So that would not really suggest that they would increase any risk of induced seismicity. But as I say, that might be location specific.
Mm-hmm. And I wonder also, if I may add one more.
Go ahead.
You showed one figure where there was a fault gouge at both sides of the fault and only at one side. Can we say something about that? If we see fault with a fault gouge only on one side?
So I think you might be referring to the fault damage zone here rather than the fault gouge. And yes, that can be asymmetric. I don't know a great deal about this. Is this more something that structural geologists who actually go into the field to look at faults, they know much more about that. But you may have two opposing materials on both sides of the fault, and one may show much more damage than the other, just because the properties of both rocks are not the same. And the fault gouge in the middle is I think that is usually a mixture of both materials then, and that's not really. I don't think that's very clearly linked to either side of the fault, of the material on either side of the fault.
Yeah, thank you.
We do have a question here from Auke, and again, I really like the question. It says, hi Sabine, for future geothermal CO2 storage operation, it would be nice if you can do those operations in velocity strengthening reservoirs. Which rock types as reservoir rocks should we go for? Because that seems to be, you can just, from an engineering perspective, we know which kind of reservoirs could be much safer now.
Yeah. Well, that's yeah, it makes a lot of sense. So what I would say is it's unfortunately slightly more complicated than just looking at rock type. That would be good, but it's also the temperature and things like the normal stress or what depth you're looking at. All these factors affect whether the stability of the faults that would be in there. So only looking at the material, unfortunately, doesn't tell you which reservoir to go for.
That's too bad. So, well, too bad for the practicing engineer, but good news for the scientists who
Yes.
have puzzles to solve. Kevin Bistum, hi Kevin, good to see you. He asked a question. Hi Sabine, interesting talk. Following Sebastian's pragmatic engineering question, wondering about fault zone geometry. Any insights in upscaling from the single fault core to, and then he corrects himself, to fault damage zones, so still at the subseismic scale?
Well, that's not something I have any experience with, to be honest. So I would still say that within fault zones, the behavior is still localized. But that's actually more a question for modelers than for me. I really look at what happens in such a localized zones and how the different zones then interact to give you the macroscopic fault behavior. I can't really comment on that, unfortunately.
Does fault geometry matter?
Yeah, I would think so. Well, again, that's not really my expertise. You mean matter for induced seismicity?
Yeah.
Yeah, I think it does. But I can't really say, like, if it looks like this, you've got more risk, or the other way around.
I hear some master's projects coming along and looking into that issue. There seem to be no further questions coming through in the chat room. We still have a little bit of time. So Maren, do you have any further questions while we're waiting? Otherwise, can give Sabine an early break.
Well, no, I don't think so at the moment.
Okay, so if there are no further questions from the audience, thank you everyone for attending the talk, for asking the questions. Sabine, thank you very much for giving us your time and for really interesting talks. Always great to see colleagues speaking. Hold on, there's actually another. So it's always like the bus. You're waiting for the buses, and then no one comes, and then they come all in one go. So going back before we say goodbye, and we take another question here. Amir Zaman, who, by the way, just handed in his PhD thesis, I've heard. So congratulations on this, Amir. Thanking you for the nice talk. Would fractional behavior repeat itself on a, I'm not sure, do you mean fractional frictional behavior here, Amir? Behavior repeat itself under several stress-distress cycles in cyclic geo operations where certain stress gets loaded and unloaded on rocks at a small scale. So we think natural gas storage or hydrogen storage, how much hysteresis is in this? process?
So I think that depends on the stress, the state of stress, right? If the stress concentrations are released by movement along the fault zone, then it might take a while before the next slip or movement would occur. But if that stress is built up in the meantime, then faults typically do reactivate. So yeah, I do think so. I'm just not sure if that would be a cycle which follows those cyclic operations very nicely.
So you think that, just to clarify, so you think there is hysteretic behavior? So if you unload, deload, unload, deload, that every time something changes in the parameters, or
that the parameters change. Okay. Well, if the material is still the same and the pressure and temperature conditions are the same, then no, I don't think that the parameters change. It's more that basically the boundary conditions can change by the cyclic behavior.
Okay, so the material is reversible, but the material behavior is largely reversible.
Not everything in the material is reversible. No. So maybe that's a bit. Maybe I took it a bit too simple, because if you have time-dependent processes occurring in a fault gouge, then actually the fault has a different starting point the next time that you start slipping it, that you start moving the fault. I think to a certain extent, yeah, there are probably some differences from one event to the next. Yeah.
Okay. It looks like we have the audience has asked all the questions they wanted to ask. So thank you again, Sabine, for a great talk, for answering all the questions. And I'm always intrigued by sort of the necessity of understanding small-scale behaviors and how complex it is, and this big challenge of how you capture these small-scale complexities into these pragmatic engineering models that allow us to make better reservoir management decisions and base these decisions on proper scientific insights. So it's clearly there's still a lot of work to be done. And Amir, just comments thanking you as well, and something nice to develop your model in there for the future. So thank you very much, Sabine. Thank you.
Thanks very much. It was a pleasure.
And Maren, do you have any closing comments?
Yeah, thank you again, Sabine. That was very, very interesting, I think, and I learned a lot.
Good.
So we're pleased to announce the speaker for next week, which is Thomas Kohl from KIT in Germany. And he will talk about new perspectives for deep high temperature underground storage in the Deep Star project. So we look forward to see you all next week again. Bye-bye.
Okay. Thank you, everyone. Thank you.